So I want to take a little bit more time and talk about the idea behind the Big Bang and some of the steps that scientists can kind of figure out on what we think happened in the early universe. And where do we get those pieces of information, which technically are things that we've talked about already in class. It has to do with thermodynamics and radiation, and then also frequencies of the way we are seeing objects move in space. So we're kind of moving back to the electromagnetic spectrum. So today I want to take just a few minutes and kind of talk a little bit about just the Big Bang in general. So let's get started. So the idea is that obviously we know the Earth is old, which therefore then makes our solar system older, and then finally after that our galaxy, and then the universe. So the universe is kind of this idea that it started out really, really small, and it's moved and gotten bigger and bigger and bigger. And so where we see it today, it's at approximately 14 billion years old. And so once again, I don't want you to so much focus on where did it come from, how did it get there, yada yada. What I'm really looking for you to understand once again is that it started out really small and it gets bigger and bigger and bigger and bigger and bigger. And as it does that, it cools off. And so where it says that it was hotter and denser than anything we can imagine, that's because all of that matter and all that energy was really, really, really close together. And as it cools off and expands, it gets further and further apart. So think of it as just like watching an explosion in slow motion. And within that, there's all these other little wheels kind of turning and moving kind of in the same direction. So that's what we're going to focus in on, is that the idea that the universe was once really small and now it's getting bigger and bigger and bigger. So in doing that, let's kind of talk about that idea of that first early universe, is that for whatever reason, it just started to expand. The idea is that it's called a singularity, where that within this one speck of energy, matter, and everything, all of this information was in there: time, space, and matter. And it started, for whatever reason, something started it to ignite, and in a fraction of the second, that speck, that object started to grow into things bigger than what we can imagine. So it started out with an atom and then got bigger, like maybe the size of your house and then your neighborhood, and then bigger and bigger and bigger until we see it to the point today where we don't really even know where the ends of the universe is. All that we know is that it is still expanding, because we can look at the rate of change in direction of how objects are moving and figure out that most of them are moving further and further outward. So as the universe cools and moves further and further away from each other, that cools off. And so we can kind of think of that as just a general concept. We understand that when things are really close together, those particles are normally going to bounce off of each other really fast, and that makes them really, really hot. But as they move further and further away from each other, that energy, that transfer of energy, starts to slow down. So things start to cool off just a little bit. And so that's where we started to find things that maybe started to form in our universe, is that as things started to cool off, matter started to form. And once again, these are going to be really, really simple. So think our protons, neutrons, and electrons. And even if we want to get into some quantum physics, this is probably where quarks and neutrinos and all kinds of different things started to form. And then we got into the idea that those started to form our atoms, and then those atoms started to combine to form simple elements. And the most simple of element formed, as we've talked about already, is hydrogen. And so these two ideas is that matter and antimatter were both formed, and the antimatter and matter would collide, and for whatever reason there was just more matter than antimatter, and so that one stuck. So over time, and this was a short period of time in these beginning steps of the universe, is that once again, as things started to cool off very quickly, those atoms, or those particles of atoms, started to kind of connect. So you had your protons, neutrons, and electrons coming together, which are subatomic particles, which are things that we've talked about. So within those first few seconds, those were formed, and once again, that formed then our simplest elements, hydrogen and helium. And as we kind of go through, we talked about with other formations of our nebula theory and star formation is that you need a lot of hydrogen in order for these huge objects to form. So if you think about in our early universe, if there was an abundance of hydrogen, you can only imagine what was the first thing that probably formed. A star. Hopefully you're thinking of that. So these huge stars started to form first, and then they would go through their process, and we know that process links back into creating a nebula that then can create a planetary nebula, which then can maybe create solar systems, or it creates another star. So this whole cycle started to continue. And if there were super large stars, also think about that's where black holes were formed. So meaning that these super large stars, once they reached the end of their fusion life, could not explode, so they imploded, and then that caused black holes that then were able to grab other parts of nebulas to kind of hold it all together. So it started this chain reaction of creating things that we now see today. Galaxies, and within the galaxies, stars and black holes and solar systems and exoplanets and all the other little itty-bitty things that we've been talking about. So to kind of go back just a little bit, after 300,000 years, the universe had cooled to maybe, and no one was here to take that temperature, about 30,000 degrees, and then our electrons started to form, and this once again allowed for those simple elements. So as you can see, I like this picture here. I think it does a really good job of kind of getting the idea is that we started from a very small little point, and as things erupted outwards, then we started to cool off, and particles started to form and allowing us to have our hydrogen and helium and the subatomic particles as well, protons, neutrons, and electrons. And then that allowed for stars to form, and then those stars exploded and either created more nebulas or created black holes, and those black holes then attracted some of those nebulas, and then you started to get these galaxies forming, because once again, remember, all galaxies are held together by a black hole in their center because they're the most massive objects in our our universe. So one of the big ideas is what we call cosmic background radiation. And so we know that radiation is just the idea that things are letting off heat or generating heat. And so back in the early 50s, there were two astrophysicists that were testing radio frequencies coming from space. And they kept getting this static noise. Didn't matter if they pointed their satellite towards Africa or towards LA or towards Alaska, they kept getting the same static noise, and they were really puzzled by it. And so where they were able to figure out is that they were actually receiving some background radiation from the early universe forming. And so think about, once again, that explosion, everything was really close together, and as things spread out, they get cooler and cooler and cooler. And this became almost just now like a faint noise that we can observe when we have an image going out. So for example, think of like a radio station or a television. When the signal goes out, you get that static noise. That's actually this background radiation from the Big Bang or from the universe. It's this background cosmic radiation. It's a microwave radiation. So remember, microwaves are on that red and orange side of the spectrum. So much longer wavelengths, which means low frequency. So this is energy that has cooled off over time. So spacecrafts and telescopes see this as a patchy pattern or slightly warm and cooler areas, and that's what we're looking at here. This is a picture of a satellite that went into space and just took pictures all around the Earth. And so it came up with this elliptical picture of what maybe early universe looked like, and the warm and cool patches. So think, once again, in space, blue and white represent really hot places, where the yellow and orange represent the cool places. So early universe was a very warm place because all that matter was pushed together. So once again, kind of just fast forwarding to what I was talking about. So if you have a place that has an area that has lots of hydrogen and that hydrogen is massed together, you're going to have gravity starting to push it together. And so in those beginning years of our universe, we think stars were the first thing to form. And once again, these would be really super massive stars. And we've talked about if it's super massive, it's going to have a high fusion rate. So these stars had a much less of a time span than maybe smaller stars. So they supernovaed, creating, once again, big nebulas or black holes. And then new stars were able to form from these other nebulas that were formed. So then we get these clusters, and those clusters would have been captured in by these black holes and then causing galaxies to form. So one of the greater ideas is that more than likely galaxies that were closer together started to collide and then made larger galaxies. So for example, the Milky Way is an extremely large galaxy. More than likely it's a combination of several other galaxies that have come together over time. So I would normally demonstrate this in class, but we're not there. So normally I would have a balloon. So just think about it. If I take a balloon and I blow it up just to maybe the size of a baseball, and then I put 2 dots on it, they're a certain distance away. And then I blow the balloon up. Those dots are going to expand further outward. And so this happens over and over again. We're able to look at objects in the night sky and figure out their distance from Earth to night, and then go back and check it in, let's say, maybe like 2 years. Normally it's expanded outwards, or the distance has gotten greater. And so this is another way in which scientists are able to suggest that the universe is growing. So we have cosmic background radiation, which shows that the universe was once much hotter and now is cooling off because we can receive that microwave radiation, that static, that thermal dynamics of radiation. And the other way that we achieve this is through what we call, I'm going to get to, oops, where is it? Redshift, which is the idea that when scientists look at galaxies all across the universe, they are normally trending to the red side of the spectrum, meaning that when we measure their distance, we can see that we are normally receiving the low frequency, long wavelengths from these galaxies that are moving. And so we call that red shifting, meaning that they're moving further and further away. And so these are our 2 ways in which that we as scientists help support the idea that the universe is expanding. One is the cosmic background radiation, with that energy being received from all around, showing that it is cooling off. And the second one is galaxies that are red shifting. And most all galaxies are red shifting away from each other, meaning that they're being pulled further and further and further out. So that's kind of the idea behind the Big Bang, is that once again we have those 2 pieces of evidence. Don't worry so much about where did it all come from. For this standpoint, I just want you to understand that it's expanding outwards. Hope that was helpful.